Hello and welcome to the video lecture on elimination reaction. In the previous lecture we were talking about the stereoselectivity, and in that connection for the E2 reaction we understood that there the strict requirement for the anti-periplanar, or if not possible then syn-periplanar arrangement of the CH and the CX bonds. Let us now try to rationalize the stereoselectivity of E2 reaction. Our example was 2-bromopentane, where we have no regiochemistry issues, but abstraction of a beta hydrogen leads to the formation of the E2 pentene, which is the major product, and abstraction of yet another beta hydrogen from the same carbon leads to the formation of Z2 pentene, which is the minor product. So now that we have understood that the CH bond that is being broken and the CBr bond that is being broken, they have to be anti-periplanar. Let us try to understand why this stereoselectivity. Is the E isomer major product because it is thermodynamically more stable than the Z isomer? No. One part of the statement is true, that E isomer is more stable than Z isomer, but that is not why this is the major product. We have to again think in terms of the transition state. These two protons that are available at this beta carbon, which have been marked as HA and HB, they are diastereotopic to each other. If you replace one HA with X, you will get a compound, and if you replace HB with X, you will get another compound. Those two will be diastereoisomers with each other. These HB cannot be exchanged by any rotation operation. I mean, you cannot exchange them by executing a CN operation. Neither can you exchange them by SN operation. Therefore, they are diastereotopic to each other. Now, one of these have to be placed anti with respect to bromine to execute the elimination by molecular elimination. So when you are placing the HB with anti with respect to this bromine, you are getting the E isomer, where in the transition state you have this type of arrangement. This is the TS for the E isomer. And when you have the Z isomer, when you have the formation of the Z isomer, you need to place HA with respect to anti with respect to bromine, and in that case you have this type of a transition state that leads to the Z isomer. So these two transition states are obviously different, where in the TS for E isomer, the methyl and ethyl, when you are abstracting the HB, placing it anti with respect to bromine, methyl and ethyl, they are away from each other, they are anti, they are also anti. The HB and bromine, they are anti, the methyl and ethyl are also anti. In this case, they are, like syn, they are on the same side. So they have started from, in the conformation, they are gauche, methyl and ethyl are gauche, and in this case they are anti. And when you are eliminating, this carbon is changing its hybridization from sp3 to sp2, and so is the other carbon. Therefore, they are becoming flat, and these two methyls will end up on the different sides of the double bond. But for this conformation to react, these two alkyl groups will end up in the same side of the double bond. So they are getting squeezed to each other, and therefore in the transition state they have steric hindrance operating between them, whereas this transition state is free. Looking at these two conformations, if you look at these two conformations, then here you have methyl bromine gauche interaction. But in this case, you have not only methyl bromine gauche interaction, but also methyl ethyl gauche interaction. So if these two conformations are considered, then the population is favoring this conformation, and the population is minor here, the population is major here. So what is happening? For the abstraction of these two diastereotopic beta hydrogens, one particular conformation which leads to the E isomer is more in population. The conformation which you require to access the Z isomer is less in population. Not only that, the transition state for the E isomer is more stable than the transition state for the Z isomer, which has to accommodate this type of eclipsing interaction in the transition state. Therefore, not only is the concentration of this compound high, but also the transition state is more stable compared to the population of this conformer and the transition state of leading to the Z isomer. So it is obviously expected that the Z alkene will dominate, because rate of the reaction depends upon activation energy. Activation energy is lower here, transition state is more stable, and you also have the situation where rate of the reaction, it depends upon the percentage population of the conformer. Higher the conformer, higher is the rate of reaction, just like concentration, no? So এটার concentration বেশি আছে, এর concentration কম আছে, so এর থেকে E আইসোমারটা হবে, এর থেকে Z আইসোমারটা হবে, কিন্তু এটা কম হবে, এটা বেশি হবে. So we understand that. Now this stereoelectronic requirement of the E2 reaction sometimes dictate that the reaction becomes stereospecific. Now this is a new term. Stereoselective আমরা দেখেছিলাম যে যেখানে মাল্টিপল স্টিরিও আইসোমার তৈরি হতে পারে, বাট only মানে only one stereoisomer dominates. So that could be enantiomer, one enantiomer among the two, therefore it could be enantioselective, or it could be diastereoselective, যেখানে diastereoisomers তৈরি হতে পারে, একটা diastereoisomer অন্যগুলোর থেকে বেশি তৈরি হচ্ছে. But what is stereospecific? That stereoisomeric starting materials lead to stereoisomeric products, which is known as stereospecificity. UPAC defines stereospecificity in this way. A reaction is termed stereospecific if the starting materials differing only in their configuration are converted into stereoisomeric product. This is best understood with an example. Say for example, we have an organohalide or organobromide which can exist in two different diastereoisomeric forms. One is that mesoisomer. Can you see that this is a meso? You have an I here, I. See, there is an I here, center of inversion. That's the meso. And here you have another one, which is the active form, that is the optically active one. The meso is optically inactive because it is internally compensated due to the presence of I. And this molecule, which is a diastereoisomer of the meso, is called the active variety. This can exist in two enantiomeric forms. I have drawn only one. If you draw the mirror image of this molecule, it will be the other enantiomer. And it lacks the symmetry elements of any second kind symmetry element is absent here. No I or sigma plane or rotation deflection axis is present here. So I have two different things, two different diastereoisomers. When we do E2 reaction under similar condition separately for these two, from the mesoisomer we get the E alkene, and from the active isomer via dehydrobromination we get the Z alkene. Why do we call it E alkene? Because priority of phenyl is higher than that of hydrogen, priority of bromine is higher than that of phenyl, therefore high priority groups are on opposing side, therefore it is E, and this is obviously Z. Recall that two phenyl groups being on the same side, you should call it the cis alkene, but cis will not always be Z, as you can see. CIP priority rule dictates that this is the E alkene and this is the Z alkene. These reactions are stereospecific because what starting material you choose, that will dictate which stereoisomer of the alkene you are going to form. If you want the E alkene to be your product, then you have to take the mesoisomer. If you want the Z alkene to be your product, then you have to take the active isomer. This is a fact which we have to explain. And secondly, the most striking feature of this reaction is that the mesoisomer reacts at a very slow rate compared to the active isomer. So we have to explain that. Why we cannot access E alkene from the active isomer, why it has to be the mesoisomer from which the E alkene has to be generated. On the other hand, why cannot the Z alkene form from the mesoisomer? Why it has to be always the active isomer which will lead to the Z alkene? Why this reaction cannot happen? Why that reaction cannot happen? So that is the question. And moreover, the mesoisomer being highly reactive compared to the active isomer, why is that? So we are trying to explain this obviously in terms of our transition state argument, and we have to note very carefully that I need to place my beta hydrogen anti-periplanar to the C alpha bromine bond. Starting from the mesoisomer, if we take say any one particular bromine, there are two bromines. You can consider this as the alpha carbon, you can also consider this one as the alpha carbon. Let us consider this as the alpha carbon. So if you think that this is the alpha carbon, then this bromine is anti, this beta hydrogen is anti. You can see that in the conformation the two phenyls are on the same side, and in the Newman projection it is clearly visible, and when you eliminate that you get the E isomer. Doing the reaction with ethoxide, it will lead to the formation of the same E isomer. If you think that this is the beta hydrogen and that is the alpha bromine, so you have the choice যে তুমি এটাকে এই ব্রোমিন এই হাইড্রোজেনকে এলিমিনেট করতে পারো, তুমি এই ব্রোমিন এই হাইড্রোজেনকে এলিমিনেট করতে পারো, জাস্ট অনলি ওয়ান থিং, সেটা হচ্ছে যখনই করবে করেসপন্ডিং পেয়ারটাকে তোমাকে অ্যান্টি পেরিপ্লেনার করে লিখতে হবে। তো এখানে দুটো ই আইসোমার একই জিনিস তৈরি হয়েছে। So from the meso isomers, placing any one of the hydrogen and bromine on its adjacent carbon anti to each other, that implies that the alkene that is being formed is of E configuration. There is absolutely no other choice. You have no choice regarding the matter but to form the E isomer, because the mechanism wants you to place the carbon hydrogen and carbon bromine anti to each other. You cannot form the Z alkene from the meso isomer. তুমি যদি Z alkene meso isomer থেকে তৈরি করতে চাও তাহলে তোমার অ্যান্টি পেরিপ্লেনার ওরিয়েন্টেশন থেকে বেরিয়ে আসতে হবে। If you think that the elimination can take place via syn periplanar orientation, then only you can get the anti alkene from the meso isomer. But as we know, যদি syn periplanar যদি anti periplanar conformation access করতে পারে তাহলে syn periplanar কেন যাবে না, and that is why meso isomer leads to the formation of E isomer. For the active isomer, the same argument can be invoked. That is, if you have hydrogen here and you place the bromine anti to it with respect to that one, or you could place hydrogen of this particular carbon anti to the bromine of the adjacent carbon. The same thing will now happen. As you can see in the Newman projection, the two phenyls are now away from each other. So that leads to the Z isomer, where you have phenyl and bromine on the same side of the double bond, and from this particular conformation also the same Z isomer. এখান থেকে যদি তোমাকে এই অ্যাক্টিভ আইসোমার থেকে যদি তোমাকে ই অ্যালকিন বানাতে হয় তাহলে অ্যান্টি পেরিপ্লেনার ওরিয়েন্টেশন ব্রেক করে তোমাকে সিন পেরিপ্লেনারে যেতে হবে। অ্যাজ উই নো দ্যাট ইজ নট গোনা হ্যাপেন because this anti periplanar orientation is happily accessed. Syn periplanar orientation, unless the molecule cannot access anti periplanar orientation, তবেই ও syn periplanar orientation এ যাবে। এখানে anti periplanar orientation there is no problem here, so the reaction will take place from the anti periplanar orientation, and the mechanism has forced your hands. You have absolutely no choice in the mechanism. So in this sense, you can say that E2 reaction is a stereospecific mechanism. It is an ongoing kind of a debate. People sometimes call stereoselectivity in terms of mechanism, that if the mechanism is such that there is no choice, or sometimes people refer to in terms of the compounds. And in this case, the two compounds, starting materials, which are stereoisomeric with each other, more precisely diastereoisomeric, meso and active, they are giving rise to two different diastereoisomeric alkanes, and meso is giving E, meso cannot give Z, and the active is giving Z, active cannot give E. Therefore, for formation of E alkene, you have absolutely no choice in this matter. You have to start from meso. For the Z alkene, you have to start from active. Therefore, these things are stereospecific in nature. And obviously, stereoselectivity definition হচ্ছে there are reactions where one stereoisomer dominates over the other in product. So automatically all stereospecific reactions are like stereoselective reactions. But as you will see, not always, or not the other way around is not always correct. That means not all stereoselective reactions are stereospecific. So now we need to explain, now that we understand that our hands are forced and we have, if we take meso, then we are bound to our fate is to generate the E alkene, and if you take the active, our fate is to generate the Z alkene. We need to explain the rate difference, why the rate is different here. In order to explain, we have to inspect the two things: which conformer is responsible for the formation of this E alkene and the Z alkene, and corresponding transition states from which the E alkene and the Z alkene is being formed. So for the E alkene, when you have taken the meso isomer, This is your conformer from which this reaction is taking place. As you can see, there is a bromine-bromine gauche interaction and the phenyl-phenyl gauche interaction, and also a phenyl-bromine gauche interaction. A phenyl-bromine gauche interaction here. So this will destabilize this conformer and its population will be low. Compare that with the active isomer, which is leading to the Z alkene. Now you can see that there is a phenyl-bromide gauche interaction, bromine-bromine gauche interaction, and phenyl-bromine gauche interaction. Now, from conformation analysis, we know that gauche interactions between like groups, that is when it is between the phenyl-phenyl and it is between the bromine-bromine, that is more severe compared to the gauche interaction between the phenyl-bromine, which are unlike group, and phenyl-bromine. So in combination, in cumulation, I should say, the phenyl-bromine gauche interaction and the phenyl-bromine gauche interaction is less severe compared to the bromine-bromine and phenyl-phenyl gauche interaction. And you have a bromine-bromine gauche interaction here, but the phenyl-bromine gauche interaction is being cancelled out. So this bromine-bromine gauche interaction and phenyl-bromine gauche interaction is less than the phenyl-phenyl gauche interaction and phenyl-bromine gauche interaction. So you have this one common, phenyl-bromine gauche interaction. You have this one common. This bromine-bromine gauche interaction, that is also common here. So the only thing that is you are left with is the phenyl-phenyl gauche interaction, and here you don't have a phenyl-phenyl gauche interaction. The phenyl groups being large and bulky in nature, this is the most severe gauche interaction that you are going to face, and as a result, this conformation A or conformation B, or you could say conformer A will be much less populated, conformer B will be much more populated. So active isomers reactive conformer is greater in concentration compared to the mesoisomers reactive conformation. So in which conformation should this molecule lie? The preferred conformation for this molecule will have the two phenyl groups apart from each other, away from each other. But if you think, that means this conformation. If you think these two phenyls are anti to each other, but therefore this hydrogen and that bromine, they are not anti-periplanar or syn-periplanar. So elimination is impossible. Neither are this hydrogen and this bromine. Therefore, anti-periplanar or syn-periplanar orientation is not there and elimination cannot happen. It can only happen if this hydrogen becomes anti with bromine, but that would mean bringing the two phenyl groups close to each other, and that would destabilize the conformation. Therefore, the reactive conformers concentration is low here, the reactive conformers concentration is high here, because that is the native conformation in which the molecule likes to exist. The two phenyl groups are away from each other. So the population is high, the population is relatively low. Look at the transition state. The two phenyl groups are being squeezed to each other because the carbons are changing their hybridization from sp3 to sp2, and there is a developing severe torsional strain and eclipsing strain in this case, whereas you have the two phenyl groups away from each other. So this transition state is less crowded, relatively more stable. So that transition state is, less stable, that transition state is more stable, that population is higher, that population is lower. So rate of the reaction is proportional to concentration, as well as depends upon the activation energy. TS being more stable and the population of conformation reactive conformer being higher, we obviously have a situation where the active isomer would react at a faster rate compared to the mesoisomer, leading to the formation of this Z isomer, Z alkene, at a much faster rate. So now we are moving into a little bit of deep waters. এটা খুব ভালো করে বুঝতে হবে. The dehydrobromination reaction of the mesoisomer of this particular compound is known as the stilbene dibromide, because stilbene is this one. You have stilbene, which is this one. If you add a bromine molecule across the two carbons, that is the carbon-carbon double bond, you get this type of compounds, which are known as the stilbene dibromide. You can start from the E stilbene, you can start from the Z stilbene, you can access the active and the mesoisomers from those things. But that is the matter which is on semester 3. But let me tell you that these are known as the stilbene dibromides. So if they ask you the question by giving you the name stilbene dibromide, so don't get confused. Stilbene dibromide that can exist in three stereoisomeric forms. Two of them are enantiomers, that's the active, and the other one is the meso. Meso gives rise to, on a dehydrobromination, gives rise to the E alkene, but we know that the reactive conformation is concentration is low, activation energy is very high because the transition state is suffering from destabilizing interactions. Given all these things, the mesoisomer dehydrobromination is so bad that given any other opportunity, it will not undergo dehydrobromination. In fact, if you treat this molecule not with sodium ethoxide but with pyridine or iodide or zinc, it undergoes, not dehydrobromination but debromination. So take for example, if you are treating a dibromide with pyridine, you have the stilbene dibromide active isomer. This active isomer will, just like before, it will undergo the dehydrobromination to give you the Z alkene. But for the mesoisomer, when you have changed the base from sodium ethoxide to pyridine, instead of dehydrobromination, it will undergo debromination. That means it is not losing HBr, but it is losing bromine, and it is producing E-stilbene. This result actually gives a clue to what is exactly happening. The first factor is probably that the reactive conformer for the debromination, where the two bromines are anti to each other, that is much more accessible for the mesoisomer than the reactive conformation which places the hydrogen and bromine anti with respect to each other. Because we have already seen that if you place the hydrogen and bromine anti to each other, then the conformer has severe phenyl-phenyl interaction, which is not good. So that conformer is less stable. Maybe when you have placed the two bromines anti to each other, because for debromination একটা ব্রোমিন কে আরেকটা ব্রোমিনের সঙ্গে অ্যান্টি হতে হবে, and that conformer will be like more populated because that will place the two phenyl groups anti to each other. So that conformer is very high in population. আগেরটার সাথে এটাকে গুলিও না, আগেরটাই আমরা একটা মেসো আইসোমার আর একটা অ্যাক্টিভ আইসোমারের মধ্যে কম্পেয়ার করছিলাম। এখানে আমরা মেসো আইসোমারের মধ্যেই দুটো ডিফারেন্ট কনফরমেশনকে দেখছি। একটাতে ব্রোমিন অ্যান্টি হয়ে বসে আছে, দুটো ব্রোমিন, তার ফলে সেটা ডিব্রোমিনেশন দেবে। আর একটাতে এইচ আর বি আর অ্যান্টি হয়ে বসে আছে, তার ফলে সেটা ডিহাইড্রোব্রোমিনেশন দেবে। As you can see, the population of the conformer that corresponds to the debromination product will be more populated compared to the conformer which leads to dehydrobromination. তাহলে এর population বেশি আছে। Phenyls are anti, here phenyls are gauche. Let us look at the transition states. The debromination transition states have these two phenyl rings away from each other, leading to the formation of the E-stilbene, where you can clearly see that the two phenyls are away from each other. But the dehydrobromination transition state, they have these two phenyls close to each other, and in the transition state there is developing a severe eclipsing interaction between these two phenyls. So this transition state for dehydrobromination is less stable than the transition state for the debromination. কাজেই মেসোআইসোমারের জন্য, given the opportunity, this is important, given the opportunity, the molecule will undergo debromination instead of dehydrobromination. And that opportunity is given when you are treating this thing with, say, pyridine, or you are treating this thing with, say, zinc, or you are treating this thing with the iodide or something like that. So if you use zinc, then you have zinc here, a couple of electrons here. So this zinc will take away this bromine. This elimination reaction will take place. This will eventually become ZnBr plus and Br minus. So eventually we will have ZnBr2. With pyridine, we have N-bromopyridinium with a bromide counter ion. With iodide, we have iodide attacking here, and therefore this is giving rise to IBr and Br minus. An interhalogen compound is being formed. All these, pyridine or iodide or zinc, they are capable of abstracting a carbon, breaking a carbon bromine bond and attacking this bromine, and eventually leading to debromination. But for sodium ethoxide, you do not have that scenario. For sodium ethoxide, it cannot attack this bromine. It can only abstract the beta hydrogen, and therefore this molecule cannot undergo debromination when you are treating this thing with a base such as ethoxide. So even though the debromination transition state lacks the phenyl-phenyl eclipsing interaction and the population for the debromination reaction is higher, sodium ethoxide simply cannot react in this manner, and therefore even though the phenyl-phenyl eclipsing interactions has to be accommodated in the dehydrobromination reaction, it undergoes only dehydrobromination. তাহলে সোডিয়াম ইথক্সাইড দিলে তুমি যাই নাও, অ্যাক্টিভ নাও, মেসো নাও, যাই নাও, সবসময় ডিহাইড্রোব্রোমিনেশন হবে। আর পিরিডিন বা আয়োডাইড যদি দাও তাহলে মেসো আইসোমারের ক্ষেত্রে ডিব্রোমিনেশন উইল বি ফেভারেবল, মোর ফেভারেবল। নাও ইউ মে আস্ক দ্যাট অ্যাক্টিভ আইসোমারের ক্ষেত্রে কি হবে? ইফ আই ট্রিট দ্যাট উইথ সে পিরিডিন, what will happen? Let us check যে debromination আর dehydrobromation এর মধ্যে কোনটা favored. This is the dehydrobromation transition state where you have the two phenyl groups apart from each other. Conformer এর population বেশি আছে, phenyl দূরে আছে। Debromination transition state will require placement of the two bromines anti to each other, and that would mean you are bringing the two phenyl groups close to each other. Therefore, severe phenyl-phenyl gauche interaction, so this is despopulated. This phenyl-phenyl gauche interaction is becoming even more prominent in the transition state, and therefore this transition state is very high in energy. Kajei, irrespective of the base that you are using, whether you are using the base as ethoxide, or you are using pyridine, or you are using iodide, or you are using zinc, it is always the dehydrobromation for the active isomer. But for the mesoisomer, it depends. If you have sodium ethoxide which cannot undergo debromination reaction, then the reaction will debromination will not take place. It will take place dehydrobromation, then that will be a slow dehydrobromation. But for pyridine or iodide or zinc, it has the opportunity of debromination, and it will undergo the debromination, leading to the formation of the E-state. So this is a segment from where all sets of questions are being set. প্রচুর প্রশ্ন দেয় এখান থেকে যে অ্যাক্টিভ আইসোমার এবং মেসো আইসোমারের মধ্যে সোডিয়াম ইথক্সাইড দিলে কি হবে, কোনটা বেশি রিঅ্যাক্ট করবে, কোনটা কম রিঅ্যাক্ট করবে, এটসেট্রা এটসেট্রা। দে হ্যাভ আস্কড all sorts of questions. So I think you should pay a little bit of more attention to this segment, because this is a little bit difficult to grasp, কারণ বেসটা চেঞ্জ করে দিলে তোমার আউটকামটাও চেঞ্জ হয়ে যাচ্ছে। Before leaving the stereospecificity, let us consider one aspect of it. If you think that the mechanism is itself stereospecific, then E2 reactions are always stereospecific, because you have absolutely no choice but to place the two eliminants, that means the CH and the CX, anti-periplanar to each other. If not anti-periplanar, then at least same periplanar to each other. But if you think in terms of the compounds, then there are examples where the stereospecificity definition kind of breaks down, because stereospecificity tells you that the reaction has to be such that one stereoisomeric starting material gives one stereoisomer of the product. যেমন আমরা ওখানে দেখছিলাম যে আমাদের মেসোআইসোমার থেকে E-alkene তৈরি হচ্ছে, and the other stereoisomer of that reactant, that is the active isomer, giving rise to the other stereoisomer of the product, that is Z isomer. And we have told you that by definition, therefore, stereoselectivity, all the reactions that are stereospecific, they are also stereoselective, because stereoselectivity means one stereoisomer dominates over the other. But is the reverse always true? That means if I have a stereoselective reaction, is the reaction stereospecific? Here is an example where we are trying to demonstrate that that is not always the case. If you have a two bromopentane, this is a chiral center, so this molecule can exist in two different enantiomers, and you are doing the reaction with sodium ethoxide. You are getting E2-pentene almost 50%, Z2-pentene almost 18%, and pent-1 31%. So this reaction is regioselective. Obviously, Z-set product is dominating as expected, because your leaving group is bromide, and the reaction is stereoselective as well, because this one is not a stereoisomer, but these two are stereoisomers. So the Z isomer is minor, E isomer is the major product. So this reaction is stereoselective. Undoubtedly, this is an example of a stereoselective reaction. But is the reaction stereospecific? If we start from the one enantiomer of the two bromopentane, that is the R enantiomer, and then we do the same reaction on the same condition with the S enantiomer, then we have these three products where we have 50% E2-pentene, 18% Z2-pentene, and 31% pent-1. The same thing is happening here. Same is happening here. The same thing is happening. The R2 bromopentane and S2 bromopentane, the sodium ethoxide, we are giving E2 pentene and Z2 pentene and 1 pentene. The same ratio of the three products are being obtained from these two different enantiomeric, stereoisomeric starting materials. Therefore, looking at the strict definition of the stereospecific reactions, one particular stereoisomer of the reactant molecules affords one particular stereoisomer of the product, while a different stereoisomer of the reactant gives the different stereoisomer of the product. This is not a stereospecific reaction, because R থেকে তাহলে এইটা যদি মেজর হয় তাহলে S থেকে আমার এইটা মেজর হওয়ার কথা ছিল, but that is not happening. We are getting the same population of the products, three products starting from either of these two starting materials. Why is that? That is because the two transition states that are involved for formation of either this one or this one or this one from this one and that one, এই দুটো এনানসিওমারের থেকে হয় এটা নাহলে এটা নাহলে এটা তৈরি করার জন্য, এখান থেকে এটা তৈরির জন্য যে টিএস, এখান থেকে এটা তৈরির জন্য যে টিএস, দে আর এনানসিওমেরিক। এখান থেকে এটা তৈরির জন্য যে টিএস, এখান থেকে এটা তৈরির জন্য যে টিএস, দে আর অলসো এনানসিওমেরিক। এখান থেকে এইটা তৈরি করার জন্য যে টিএস, এখান থেকে এইটা তৈরি করার জন্য যে টিএস, দে আর অলসো এনানসিওমেরিক in nature. For each of these three products that we are generating from the two different enantiomers, and consequently for all three products, for each of the three products, we have two different transition states, one starting from the R, the other starting from the S isomer of the starting material. They are enantiomeric to each other. Look at these two transition states. We have taken S2 bromopentane on the left hand side. We are eliminating HBr by placing this hydrogen anti with respect to bromine. We are going to get the E2 pentene, and if I the same E2 pentene is made from the R2 bromopentane, then we have to place this hydrogen and that bromine anti to each other. And when you look at the two transition states, these are enantiomeric in nature. They are mirror image to each other, but they are not superposable to each other. And if the transition states are enantiomeric and your starting materials are enantiomeric, we know that the free energy of enantiomers are same. Therefore, the activation energy for accessing this transition state from the S2 bromopentane and accessing this transition state from the R2 bromopentane, their activation energies are same, because these two are same. So you have this R and you have this S. You have this transition state from R. You also have this transition state from S. R and S, they are enantiomers, their energy is same. TSR is mirror image of TSS, non-superposable mirror image enantiomeric to TSS, therefore their free energy is also same. So the activation energy for the formation of the TSR, accessing the TSR and TSS, will also be the same. And therefore, how can a different amount of E2 pentene form starting from S isomer and from R isomer? It cannot. It will always be the same percentage population of the three products, irrespective of the starting material, whether you take the R or the S isomer. And therefore, we are forced to say that this is a stereoselective reaction. Undoubtedly, it does stereoselective. 51% of the product is one stereoisomer, only 18% of the other. But this reaction is not stereospecific in a sense. If you define stereospecificity in such a way that stereoisomeric starting materials will give rise to stereoisomeric products. Which stereoisomer or product will dominate, that will depend upon the starting stereoisomer. যেমন আমরা ওখানে দেখছিলাম যে আমরা এই সিস্টেমের জন্য আমরা দেখেছি যদি আমাদের ই আইসোমার তৈরি করতে হয় তাহলে মেসো থেকে শুরু করতে হবে, যদি জেড আইসোমার শুরু করতে হয় তাহলে অ্যাক্টিভ থেকে শুরু করতে হবে। বাট দিস ইজ নট দ্য কেস। আমি আর থেকে শুরু করলেও 51%, 18% এই রেশিও পাবো, আর এস থেকে শুরু করলেও একই রেশিও পাবো। So this reaction represents an example where the reaction is stereoselective but not stereospecific. So it is not always true. This stereoselective হলে stereospecific হবে, but however stereospecific মানে by definition সেটা stereoselective হবেই, তার কারণ stereoselectivity definition এ বলা হয় যে one stereoisomer dominates over the other, as you are seeing. Stereospecific মানে তো তাই। So I hope that this important concept has been understood by you. Listen to this video lecture multiple times if you have any confusions, and please consult with me if you have any confusions. I thank you for your patience, and I will be seeing you in the next one.